Okay, anyway, very quickly to repeat. So Python is climbing up fast here. C is on the top, and then yeah, what I want to say. So that this one, Java is still important, goes down a little bit. Python is coming up fast, and C is very important language, and others didn't make the cut. So sorry, forgot to share. Next time, please, please, please tell me that I'm not sharing. I don't know how I didn't see it. Hey. Sorry. Yeah, very important. Unmute your microphone. Give me a feedback, because this teaching is not easy. Okay, so this is what I was trying to explain. Let me repeat once more. So the idea is that here I'm showing Mandelbrot set, and we're gonna use this operation. F of z is z squared plus z naught, and we're gonna apply this f. We're gonna evaluate f of zero, f of f of zero, f of f of zero, so many times. We're gonna repeat this until n goes to infinity, and then the question is whether this sequence remains finite or explodes. So basically, the value becomes finite, remains finite. Then this thing is in Mandelbrot set. That z naught is in Mandelbrot set. But if the value goes to infinity, then number is not in Mandelbrot set. So basically, we do the following: we start with f of z at the first iteration, f1 of z is equal to z naught. Then in the second operation, we're going to square this. f2 of z is then square of this, isn't it? Which is z naught square, again plus z naught. And then at the third iteration, we're going to do f3 of z is square of this thing plus z naught, and so on and so forth. So f of 4 and so on. So the question is whether fn of z is less than infinity or it's bigger than infinity. So if this is less than infinity, then it means that we remain. This is part of the Mandelbrot set, is in Mandelbrot, and if it's bigger than infinity, then it's not. Okay, so how we're going to figure this out? Well, we're going to take n to be some large number, so let's say 1,000. We repeat this operation 1,000 times, and we see if z, absolute value of z becomes bigger than 2, then once absolute value of z is bigger than 2, we can be pretty sure that the sequence will go to infinity, which means that it's not in Mandelbrot set. But if absolute value of z is less than 2 after, let's say, a large number of iterations, such as 1,000, then we can say that yes, it is in Mandelbrot set. Okay, and then we plot here. For example, we're plotting with the color coding basically 1 over the number of steps that we survive this operation, and therefore the black stuff, the black thing, is basically close to black thing is basically means that for a large number of iterations we survive this operation, and therefore it's in Mandelbrot set. And other colors tell us how long we survived this operation. The value of z was less than 2. Okay, so we're going to do this now. We're going to do this plot in many different languages. So we're going to start with Fortran, then with C, then with Perl, then with Python, and we're going to see the difference between those languages. And this will also help us to check whether our installation of all the codes of all the necessary applications is good. Any questions about that? Good, it's easy, huh? Okay, so let's start with the Fortran implementation. I know this is very old-fashioned, but still sometimes it's a good idea to be able to read Fortran and see roughly what it does. Yeah, how do we get the codes from online? I mean, we're not going to be able to, we're not going to code this in real time right now for the first exercise. You can download the code. So one way is to go to our homepage and click on this local copy, plots Mandelbrot set using Fortran, C++, Perl, and Python. You click on this, and then you can either download the entire tgzip and unzip it, or you can download every piece separately if you want to. Maybe the easiest is to download the entire tgzip. And then if you download the entire tgzip, you do a tar xzvf and the name of the zip file, whatever it is. It's compare. So in my case, it would be download compare languages tar. Mine is already unzipped, so my xvf, then it will work, because Mac, it turns out when it downloads, it unzips it automatically. I'm not going to do this now because I already have them here, but if you don't, then you unzip and you can use it. So what should be in there is basically Fortran Fortran code, C code. There is makefile provided for both Fortran and C. Then there is a Perl implementation, Python implementation, and then some more fancy Python implementation that we're going to go through. Okay. So if you want to compile this, you can, for example, type make, and it's supposed to compile on my computer. That doesn't not necessarily mean that it's going to compile on your computer. You might need to tweak a little bit the makefile. But if you have an almost identical installation to mine, then it will work instantly. Okay. Now let's go through different codes. So I opened here the Fortran code, but I'm going to rather explain it here on iPad. So what do we do? So we are going to first write a function, Mandelb, that takes as an argument this z0, which is the complex number in the complex plane. The entire plot here is basically plotted as imaginary part of z0 and real part of z0, isn't it? So we're going to have a fine mesh of real part of z0, imaginary part of z0, and this is going to be an input to this function. And then max steps is this n that I was discussing before, how many times we're going to iterate this operation. And typical n that we're going to use is a order of 1,000. Now, what do we do in this function? Well, this is the main do loop. So in Fortran, the repetition is usually done with so-called do loop. In Python and in C, we usually use for loop. In the equivalent loop is called do in Fortran. Okay, so we're going to go from 1 to max steps. We're going to repeat this. And what that is? Well, we, of course, apply this operation z squared plus z naught. It's not z times z plus z naught. And the new z becomes z times z plus z naught. Okay, that's this function f of z squared plus z naught. Okay. And we repeat this many, many times. However, we check every time inside the loop if absolute value of z, so if absolute value of z is bigger than 2, then we know that this is outside Mandelbrot set, okay? And then we can immediately instantly return. So the question is what to return. We could, of course, return some large number, for example, but for nice plotting, we're going to turn the number of steps that we survived, okay? So, which means that if we return very large number, it means that we are most likely in Mandelbrot set. So at the very, very end, we're going to return the max steps, which means that returning large number means that this particular point is very likely, or yeah, it's very likely part of the Mandelbrot set, isn't it? Now, in the interesting thing in Fortran is that when we return here, return means go out of the loop, go out of the function. Okay, this is similar in all other languages, in Python and in C. But the difference is that in Fortran, when we return, we don't give we don't add here a variable that we return. However, we need to set the name of the function. The name of the function, you see, this name of the function is Mandelbrot, and we need to assign to this name of the function the variable that we want to return, which in this case is I minus one. So we're going to return I minus one, and we're going to set it to the name of the function. That's convention in Fortran. And then we just return. The reason that we return I minus one, not I, is because we want to be compatible with C. In C, usually the loop starts with 0, and therefore we return one number less. Okay, so I guess this is pretty simple function, self-explanatory story kind of. And so what do we need to do? We need to now set up the main part of the code, which is going to use this, which we're going to call this function many times. No, yeah, for each z naught, isn't it? So this is the main part of the program, Fortran program. It starts with a program, name of the program, some name, and then end program. And this is the main loop here. So do and do and do and do. So this sets up this our complex number z naught, okay, which is the complex number in xy plane. So x and y, isn't it? And the loop I here uh, corresponds to the x direction. Yeah, so we're going to use I here, and here we're going to use in y direction we're going to use loop j. Now, what is x here? We use x. X is defined in here, which is basically the range for the plotting. So in this case would be this is minimum and maximum x. I think it's minimum x, maximum x, minimum y, and maximum y. So now you see that from with this information of the minimum and maximum x and minimum maximum y and I and j, we build x and y, which is now in the complex plane. And then we give this complex, we give this, from this x and y, we create a complex number z naught, and we give this to the function that we just produced before, and then we remember this in a two-dimensional array. So we save this in two-dimensional array. So this two-dimensional array is an array of real numbers, okay? And you see the nice thing in Fortran is that it's extremely easy to manipulate multi-dimensional arrays. All you need to do is to write this in brackets the dimensions nx and y. And as long as nx and ny are defined, in this case 1000 by 1000, this will immediately allocate two-dimensional array or any dimensional array, and you can use it. This is something that, of course, is also easy to do in Python, but it's not that easy to do in C++, for example. Yeah, now the question is, why do we bother to kind of save this two-dimensional array? Why don't we immediately print this, let's say, to a disk and then display the plot? Of course, we don't want to plot anything in Fortran, but we're going to write to the disk and then we're going to display that. The reason for this is because we want to use timer. Printing typically takes as much or even more time than calculating in this case. Therefore, we want to separate the calculation from printing, isn't it? And we're going to use timer to see how fast is Fortran execution versus C execution versus Python versus Perl and so on. And in particular, we're going to This loop is going to be speed up with OpenMP. I mean, I mentioned last time the so-called OpenMP multi-core execution. And here is this directive, OpenMP directive, that makes execution on um, several cores fast. So basically, both loops, both I and J loops, will be executed on as many cores as you want, as many cores as your computer has, or more. We will see how to tune that, how many cores to use. But the important point is that we just basically two lines of code, which look like a comment. So this symbol here is basically a comment. Um, uh, with this symbol, we can make this OpenMP parallel. And the syntax is very easy. All you need to do is to write this symbol OMP parallel, OMP parallel do in front of the do loop that you want to parallelize, and you need to end the whole thing with OMP end parallel do. And now the only slightly non-trivial thing is this private and then variables. So does anybody know what would this mean? This private and some variables? Do you have any idea?
Doesn't it mean that it's only accessed by the specific thread that you instantiated, so it's safe to like instantiate copies?
Absolutely, yes. So the important point is that different cores or different threads, it's called threads, but basically you can think of it as a core, will have different I. So this variable I will be different on different threads or different cores. And therefore, consequently, also J will be different because different cores will execute in their own way this particular code. And therefore, X needs to be different on different cores, and Y needs to be different, and Z naught need to be different. And all those variables needs to be then specified here in the beginning that they are private. Because if you don't do that, then different cores will try to use uh, the same variable. So in other words, by default, in OpenMP, everything is shared. Everything is basically, all the cores will compete for the same memory location. Um, so therefore, we need to specify those variables that are not shared, that need to be different on different cores. Those variable needs to be explicitly specified to be private. Okay, we're going to come back to this OpenMP syntax later on, but for now, the important message is that very little code will add this OpenMP parallelization of the loop and will allow us to run it on multiple cores. Now, in addition to this OpenMP, we also have we have this timing here. So we're going to have two times. One is going to have we're going to save time in the start and start W, and the other one is finish and finish W. Now, what's the difference between these two? Yeah, and then we're going to print out the difference in times between finish minus start and finish W minus start. So the difference in these two timing is that one looks at so-called wall time and the other one clock time. So what's the difference? Well, um, wall time is the time the way it's perceived by a human, or if you have a clock on your wall, that's what the difference in time is going to be if you look at your clock on a wall. But the clock time is a different thing. So if you have many threads, clock time is going to be bigger because it counts how many uh, CPU ticks the code used. So if you have 10 threads, then clock time is probably going to be 10 times bigger than the wall time. Okay, and it's a good idea to look at both. So the wall time is the time the human would perceive how long something took, isn't it? Like clock time, however, is a bigger number. Okay, so Yeah, this is all that has. This is the entire execution of the important part of the execution of the code. Then what is left here is only printing. So we're going to repeat once more the loop over all points. We're going to once more create x and y, and then we're just going to print out the content of this array. And instead of printing number of steps, we're going to print 1 over the number of steps. So basically, in this case, large number, if the number here is 0, this means that the value is in Mandelbrot set, and if it's bigger than 0, uh, then it's probably not in Mandelbrot set. Well, 0 here means 10 to the minus 3 because I is going to be 1,000. Okay, so that's what we're going to print on the disk, and then we're going to display this with GNU plot. Now, in order to do that, we first we need to compile the code, and here is the um, compile command. So I'm going to use gfortran. So gfortran minus 03 means maximum optimization. There is 00, 01, 02, 03. Now I'm going to use Openmp, fopenmp, for Openmp execution. And then minus O means the name of the executable. Minus O means output. And then finally, I'm going to write name of the file, f90. Now, if you don't want Openmp compilation, you might remove this f of Openmp, but unfortunately, compilation will not work. So, for example, if you didn't yet manage to install Openmp, you might remove this Openmp option, but unfortunately, my compilation doesn't work because it cannot find this particular clock time. So I'm using this Openmp get time and Openmp get time. So this is, if you don't have Openmp, then this you need to comment out this line. So we need to comment out this particular line, this line and that line. And I guess also use Openmp lib. So if you comment those out, then the code will work even when you don't have Openmp installed. But let's assume we have, so then minus Openmp will compile this. And then we have this executable here, mount f, and we can execute it. Now, I don't want to execute it without storing this final result on a disk, because otherwise it's going to print on the screen, and that will create a lot of printing, and it's going to take forever. We don't want to do that. So this command here, pipe into a file, will print this into a file rather than on the screen. Okay, and now I'm executing this, and we see that the clock time is 1.3 and the wall time is 1.2. That means that I probably used just one core. I mean, the two are not exactly the same, but because there's some error of how the time is being measured. So now if I want to use more than one core, what I do is I write I change the environmental variable OMP num threads is equal to number of cores. So 1 means 1 core. So now it should be more or less the same as before. Yes, so I'm using 1 core. But if I change this, yeah, export here means that I'm gonna set an environmental variable, not just, well, for this shell and also any other subshell that I might create later. So with this particular command, I'm changing this particular environmental variable on my computer. And I can set it, for example, to 10, which means that I'm going to now use 10 threads on my computer to execute the same code. And if I do it now, I see that my wall time is substantially smaller, 0.5. Actually, before it was even smaller, like 0.25. But the point is, it's substantially smaller because several cores are being used. Yeah, like it can go.
Hi, Professor.
Yes.
Can you explain again what's the differences between clock time and wall time?
So wall time is the time that you as a human perceive. Okay. So you see, if I execute now, it's only 1/4 of a second, isn't it? Okay. So if I have a wall, if I have a clock on the wall, it will show me that that it took 1/4 of a second right now, doesn't it? If I have new threads is 1, then clearly it takes more time, isn't it? Okay, now it's 1.5 seconds. It doesn't take quarter of a minute. So wall time is what we perceived as a time. Now clock time, however, is the time number of clock ticks that the code needed or the code used. And of course, if you have more threads or use more cores, then of course more time is being used. Okay, if I use 10 cores, then 10 times more clock ticks are being used. Okay, so it's basically clock ticks that were used. Clock time is number of clock ticks that were used, the cumulative number of clock ticks that were used by this executable. Okay. Yeah. So the important point is that the code doesn't immediately finish when it prints the time, because it still needs to write the content on the disk, and that takes quite some time, unfortunately. But now we have the file man.dot, which has the first column is x, second column is y, and the last column is this 1 over number of iterations, isn't it? Which can be between 0 and 1. And now we want to display this and see how the Mandelbrot set looks like. In order to do that, I prepared something which is called GNU-sh that uses this man.dot and displays it into the screen with gnuplot. Of course, you can do it with many other codes if you want to, but or many other programs. I'm using gnuplot. So I'm going to use this GNU-sh by the command gnuplot GNU-sh, and this will display the content. Yeah, gnuplot, unfortunately, for this for these large arrays is not that fast. It takes some time. Okay, but eventually it displayed properly the Mandelbrot set. Trying to make it slightly bigger. I don't know if that's easy. Takes some time. Yeah, kind of not easy. A little bit once more. With this plus command, I think I should be able to increase it a little bit. Not easy. Okay, so what I wanted to say is that you clearly see this fractal plot, isn't it? Where, yeah, now it's increased. So it's obvious if you start with z naught being 0 and you repeat this forever, then point 0 will always remain small, which means there is definitely a Mandelbrot set, and also all these points that are black are part of the Mandelbrot set. Okay. Of course, if once the number is equal to 2, we know that, or the absolute value of z is equal to 2, we know that this is not part of the Mandelbrot set. This the black region here is clearly fractal, so has so-called self-similarity. So basically, this little region around here, it's very similar to the original plot of Mandelbrot set. Now, you probably heard of this, but let me show you how you can zoom in and see that this is fractal. So there is a code, one of the executables here is called mandp dynamic, which is the Python dynamic code that you can zoom in and zoom out. I hope it works on your platform as well, on your computer. But this one is basically, we plot the same thing with Python, and we're going to discuss later on how exactly the code is done. But you see, Python actually plots this much faster, so it's very easy to zoom in and zoom out the plot. And the nice thing here is that because it's dynamic, we can zoom in small region here. See, I'm now selecting a small region here at the tip of this fractal, and I can zoom it, and you see it's self-similar. You see that I have the almost identical plot. You see that? Okay, you see. So this is the first type repetition. But now I see that there is another one here that it's also similar, isn't it? And I can select this one, this little one, and zoom in, and wow, the same fractal, isn't it? So this is called self-similarity. And you can go infinite number of times, and you will see, well, mathematically you should be able to do it infinite number of times, and you should always see the same pattern. And the interesting thing is, this is not only this little thing on the left corner. You can, for example, select a pattern here, down here, for example, okay? And it has the same property. So it's self-similar, okay? You see? And now I can select it once more. You see this little tip here? It's also self-similar. Okay, and now I can select this one third time, and I see the same pattern, isn't it? And I can select once more here, and I see the same pattern. Now, however, you see that somehow the pattern is deteriorating a little bit, in the sense that it's not so sharp. It gets less sharp with time, huh? When you repeat this several times. And then this is basically one more time. Eventually it's gonna get kind of blurred. You see, now it doesn't look anymore like original one. Okay. Mathematically it should, of course, but on a computer it doesn't. Do you know what's the problem? What would you think? Can you
Variables
answer?
with finite precision.
Yes, that's part of the problem. Yes. There are two issues actually, and sometimes we need to experiment with two to figure out which one is more important for a particular region of the plot. So one is finite precision. So sooner or later we are going to get into trouble with the precision of double numbers that we're using. And there is the other one, which number of iterations that we do. So we need to have very large number of iterations. Sometimes it's just the problem that we have around 1,000 iterations now, and we might need 10,000 or something. So if you want to improve the plot after n being large of these repetitions, we need to do two things: increase number of those repetitions, or we might run into trouble with the precision of floating point numbers. Yeah. But mathematically, of course, we should be able to do this forever. Yeah, so it's a little bit fun to play with this. Now, of course, this plot we're gonna create later on with Python. What is it? Python library for simulations. Okay. For now, we are gonna just write the result to the disk, and then we're going to display results with a GNU plot, which is a little bit more boring, but it's probably a good way to start. Okay. Any questions up to now? Questions? Too easy?
Yeah, I have one. I noticed that you use LL instead of LS to look at the document, but yes, that doesn't work in my
Yes, sorry. On my computer, LL is alias, okay? So basically, I need so many times ls minus l. Ls minus l is basically a long listing, isn't it? Ls is prints like that, and it doesn't show you the permissions and each file in its own line. Somehow I like this long listing, and therefore ls minus l is the same as LL. Now, how do you do this in your system? Well, it's very easy. All you need to do is write alias LL equal to ls minus L. Okay, and now from now on, LL is ls minus L. If sometimes you, well, okay, yeah. Now, if you want to save this so that it stays forever, you need to write this into either, I don't know whether I have profile or, yeah, I think profile will work, yeah. Into profile, for example, I have here ls minus L capital F, for example, it's my, I guess it's my LL. So you have to write certain commands like that into your .profile file, and then you can save this. That next time when you invoke it, invoke the shell, it's gonna, yeah, it's gonna work.
Thank you.
Okay, so we displayed this with GNU plot. Now we can go, yeah. Okay, so what was inside this GNU command? I guess I showed you very quickly. I don't want to go into details of how to plot with GNU plot, but the point is that we kind of set the, with the set view map, we show which color mapping to use. And then splot is basically this density plot. And we display the data from the file. With certain palettes, and yeah, so it's kind of simple Python plotting that we're going to use for Fortran and for C. Now, well, why do we still use Fortran? Maybe somebody would ask, why do we bother with this old-fashioned language? Well, one of the reasons is that there is a lot of old scientific code written in Fortran, and many times we are asked to kind of use some of this old-fashioned old code, legacy code, which is still very fast, hard to change, but it's still very fast. But more important is that we're going to use so-called F2Py or F2Py3 to speed up Python. Okay, so you can write little snippets in Fortran code, and then there is this F2Py, F2Py3 that can very quickly incorporate this as Python module. Now, on my computer, F2Py and F2Py3 are actually one and the same executable. They're not too different. If your installation has both Python 2 and Python 3, then it might be that F2Py is related to Python 2 and F2Py3 is related to Python 3. On my computer, I abandoned Python 2, so both are basically the same thing. They are combined with Python 3. Okay, so that's about Fortran. I mean, we are not going to see Fortran much more. It was first and probably, yeah, we're not going to see it. We're going to discuss much more. Now we're going to show C++. How many of you are familiar with C++? How many? Any hands? One hand. Just one. Wow. Yeah, I guess C++ is not that popular anymore, huh?
I'm familiar with C, but not C++.
Oh, okay. C is also fair. C is fine. I mean, it's the same, more or less. Yeah. We're going to do this quickly so that you can kind of compare how you like one language versus the other. And what I wanted to demonstrate with this exercise is that there is an important difference between interpreters and compilers. So compilers are so much faster than interpreters. I mean, really orders of magnitude. And compilers, of course, are C++ and Fortran. These are the compiled languages. I mean, they're kind of more clumsy to write, but they also give you something, give you speed. And you can't beat compiler, of course. Okay, so C++ compiler. C++ is a compiled language, which means that you have the source code and then you have to compile it and you get an executable, and then executable is really fast. So how does the code typically look like? Well, it's very similar. Well, we're going to write it in a similar way that the Fortran code. We're going to have a subroutine Mandelbrot. Now in C, there is no difference between subroutine of in function. Everything is a function actually. But here we write what we're going to return. In this case, we're going to return integer. If we wrote here that we are going to return so-called void, then it means that we don't return anything. So void means return nothing. But since we need to return something, we're going to return integer. And then you see that in C, we're going to use this curly brackets. This denotes a unit in C or in C++. In Fortran, we have to use this end do or end Fortran end function and so on. But in C, we use curly brackets. In Python, we use just indentation, doesn't it? So every language has its own way of doing this. Okay, and then we have this for loop here. So for loop is instead of do loop in Fortran, we have a for loop, and we're importing curly brackets, starts and ends with curly brackets. And in C, we always use starting index starting with 0. Okay, not with 1 but with 0. Can somebody do you know why we start with 0 in C rather than 1 like in Fortran? So all the loops tend to start with 0 in C and with 1 in Fortran. Do you know why? Yeah, so this has to do with arrays. There is fundamental difference between accessing arrays in C and accessing arrays in Fortran. So if you access an array in C, then let's say that A is an array. A of 0 means the first memory part or the first item in the array. Okay, this is C or C++. But in Fortran, you have to write A of, actually you have to use the other brackets, A of 1, and it looks at exactly the same part of the memory. Okay, so the first item in Fortran is always A of 1 or 1, and in C it's always 0. Okay, it's a convention. It's an, how can I say, it's an unfortunate that the two choices are different, so it's very confusing. And therefore, some people are Fortran-like. They always think with starting with 1. 1 is the first number, and C people always think that 0 is the first number. Okay, Python also starts with 0. Python is like C, but we typically start loops in the same way that as arrays. 0, 0 in C and 1 in Fortran. Okay, so we are looping here from 0 to max steps. Max step is, of course, some large number, like 1,000. And we will check if this absolute value of z is bigger than 2, then we return I, which I is how many steps we survived before we figure out that this is not part of the Mandelbrot set, isn't it? And then we return. Return means we go out, isn't it? We go out of the loop, out of the function, gone. But if we don't return, then we need to update z. So new z becomes z squared plus z naught. Like we're repeating this. Okay. And at the beginning, we need to set z to be 0. And here, this particular statement does two things. It not only sets z to 0, but also defines z. Well, both Fortran and C are compilers, which means that every variable needs to be given a fixed type. Okay, so compilers means type is fixed, needs to be given at the beginning. Well, somewhere in the code needs to be given what type this variable is. And we need to specify here that z is a complex number. Now, in C, there are several ways, several types of complex numbers. There can be complex of double. Double means like a floating point number with double precision. It could be complex number of float. Float turns out to be also floating point number, but with single precision. So double is with double precision, float is with single precision. But you can also specify complex of an integer, in principle, if you want to. I mean, this is not very common use, but it's possible. Complex of an integer would be possible. So it means that any measuring part of a number are integers. So this is so-called template in C++, which means that you can have some type which is derived from some other type. Now,
may I ask a question?
Yes, please.
Yeah, so in the argument of your function, so why you have an and symbol after the double?
Sorry, why do I have what?
The constant complex double and it's some and symbol here. Why there is such a symbol?
Yeah, this one.
Yeah.
Yes,
exactly.
That's very important. Yes, exactly. Let me think. Is it important? So this is there are two types of calling variables. One is called by reference, and one is called by value. Okay, so this particular symbol means that we call by reference. Okay, if we don't put the symbol, then we will call by value. Okay, so now we are using call by reference. What's the difference? The difference is that if we call by reference, if we put the symbol there, that means that if z0 is changed within the function, then it will change also outside globally. Okay, if we call by value, if we don't give this this symbol, then if z0 was changed inside the routine, it would not be updated outside. Does it make sense?
Yes, that makes a lot of sense. But actually, what I find in the function is the z0 doesn't change, right?
Yes. Yes. So why did I use call by reference?
Yeah.
Why did I use that? Well, that's for efficiency. Okay.
Okay.
The point is that if you call by value, so if you have an integer, isn't it? We almost always call by value. Why? Because an integer is basically so cheap that the compiler allocating a new integer is so cheap that the compiler will always optimize it out. Okay, but complex number is derived derived type. It's not a simple type, and because it's derived type, compiler might not be able to optimize it out. And therefore, when we call it by value, when we make a new copy, basically call by value means we make a new copy and work on the copy. For derived types, making a copy is expensive. I mean, it's not terribly expensive, but still, it takes some time. So we want to make and therefore we rather call by reference. But then we apply, we put here const, okay? And const means you are not allowed to change it actually. So const reference is completely because of efficiency. It has nothing to do with the fact that you want to change the variable, doesn't it?
Okay, I see. Yeah, thank you.
Yep, great question.
So, Professor,
yeah,
if the value of z0 is changing within the function, then you wouldn't write const, you would define that as var.
Exactly. So if the value was changing, then you're not allowed to use this const in front. Okay. Now what's going to happen is that, let's say that I want to write here z0 is equal to, let's say that my code would be like this. I would say z0 is equal to 1 somewhere. Okay. If I do that, I could do that. And then I compile this and I will get an error. The compiler will say, well, you're not allowed to do that because you assigned this thing to be constant, isn't it? So therefore, it's a good idea to use this concept of constant so that you don't make mistake when you have a large function and somebody might make mistake and change some variable that is not supposed to be changed. So it's a very, very good idea to use constant wherever possible. Okay. Yeah, so this is C++. So at the end of the day, if we survived up to here, then we return very large number, which in this case is max step, is the biggest number that we survived. Yeah, then we need the main part of the code, which is like important before. In C, we always start with main and then brackets, curly brackets. Main usually returns integer in C. Integer, if it returns 0, it means that there was no error. And if it returns a number which is non-zero, it means there was an error. Okay, and this return value usually a system can track and it can tell the user that there was some return value, and then there might be a manual that explains what this return value means. This is convention, it's not essential. You can also return void, but by convention, usually C or C++ codes should return some value that means something to the user. Yeah, what else? So then we are going to specify here nx and ny to be 1,000 by 1,000 grid of Z0, isn't it? Then we also have here the minimum x, maximum x, minimum y, maximum y, isn't it? So minimum x, maximum x, minimum y, maximum y. And now, as you notice, in C++, you can specify a constant array. This is actually a constant array with this curly brackets. So with curly brackets, you can initialize an array with given numbers. So curly brackets here, in curly brackets, initialize an array. Okay, and you don't need to specify here how big is the array, because compiler will figure out that it needs 4. Normally this would be 4 here. You need to specify how big the array is, but you don't need to. Was there a question? No, no question. Yeah, so what else? Then we have here this loop over I and j, just like in Fortran, where we go over the complex, the grid of the complex plane, isn't it? Grid of the complex plane, so I and j. And we assign value for x and y, and then we create complex number out of this x and y, and then we call our function, and then we save this into an array. And now, as you notice here, this array is not two-dimensional array in C++. I didn't use two-dimensional arrays. I used one-dimensional array. Okay, why did I use one-dimensional array? Because unfortunately, C++ does not have native multi-dimensional arrays. They do not exist. Native multi-dimensional arrays do not exist. So what exists is vector of integers, for example, or vector of double numbers or whatever. Vectors exist, and vectors are one-dimensional arrays. But multi-dimensional arrays are not native in C++. And I guess that's one of the reasons why C++ was not adopted by the computational community. But anyway, we can use it in this way. Of course, every one-dimensional array can be converted into multi-dimensional array, but it's an awkward way of accessing it. Okay, and now finally, Openmp Polarization. So in C++, Openmp Polarization is really easy. All we need to do here in this particular case is just this pragma statement, pragma OMP parallel 4. We use this hash here as well, it's not really a comment, but it has in C++, it needs to be hash symbol. And you notice here that in C++ we don't specify private variables. No need. Why? Can somebody tell me why? Normally you would say that we need to specify here private and something, isn't it? So we don't. Why?
Sharing.
Do you know? Anybody knows?
I'm wondering if it's because it uses C++'s scoping rules.
Yes. Yes. So the reason for this is because x and y here, for example, are local variables anyways within the scope, as you said, scoping rules. So they are defined in this within this statement, isn't it? They live both x and y live only within this little statement, within this for loop. So it's called a scope, and therefore they are not global. And because they are not global, they're obviously private to that loop. So we don't need to specify anything. They're already private. And then J, of course, here is also defined inside a loop, which means it's also private. And I, of course, is also private to this loop. So all the variables are already private to this loop. So we don't need to specify anything. The only variable which is shared is, of course, the vector array, but this one has to be shared anyway, because all different cores have to write into the same variable, isn't that the same big array? So every core or every thread will feel part of the array. You know? So that's how it needs to be done anyway. So in other words, we don't need to specify any variable to be private, because already all the variables that we need to make private are already private. Okay. Yeah. Otherwise, this is the entire for loop, and then we also use both clock and wall time in C. So in this case, we need to use OMP get W time, which is wall time, or we can just use clock, a standard routine, to get the clock time. We do the same for the end, and then we calculate the difference in time, and we also print out the wall time and clock time. Now, printing in C++ is a little bit different. So we are actually throwing things into so-called stream. This operation actually throws things on a stream, and then printing is actually one of the, it's called the output stream. We're not going to go so much into details, but printing is somewhat unique in C++. Yeah, this one, this actually means that we are printing into so-called standard log output rather than standard output. So cout means print into the screen, and clog means print into the log screen, or it's called. There are three types of outputs. One is the standard output, which prints directly on the screen, and one is in buffers. It's so-called buffers output. Then there is standard log output and standard error output. Error, of course, is clearly for errors, and log is for logging information. And the difference between the standard output, which prints to the screen rather than error output, is that error is not buffered. So immediately when the error occurs, it needs to immediately split out to the system that something happened, error occurred. And log is the same, it's also unbuffered. So it means immediately when we get to the statement, when we come to the statement, we immediately split out the result. While if we print to the standard output, then it's optimized for fast printing, which means that it prints only after sufficient amount of data is thrown to the standard output. Okay, and so of course here we repeat again this printing to the standard output, which we're going to redirect into the file. Okay, so how do we compile this code? Similar than that in Fortran, except that we invoke G++. I'm going to use -10 because my G++ compiler is the G++, as you remember, is Apple compiler, which doesn't support Openmp, while G++ -10 on my computer is GNU G++ compiler that supports Openmp. And then I'm going to add this fopen Openmp, and -03 again is for optimization, and then -o the name of the executable, manc, let's say, and then manc.cc, and this compiles. So I have here manc executable, and then I can it's called monc. I can then redirect this. I can execute and redirect into the month.dot. And as you can see, this takes 1.3 seconds to execute, which is very similar to Fortran code, almost identical. But that's because I use one core. If I specify here that I use, let's say, known threads to be, I don't know, 14. Well, I have 8 cores, which I guess 16 would be the best. Then I use 0.28 time, or 0.28 seconds, maybe 12. Yeah, okay, 0.28, which is similar to Fortran. So the important point, the important message that I want to give here is that Fortran and C are compatible in terms of speed, more or less the same, and very fast, of course. Now, of course, we can use now GNU-plot to display results, but believe me, the plot looks identical. Okay. Yeah. Any questions up to here? Any questions? Too easy? Too simple?
I guess there is a typo on your slide, right? It should be MANDC, not MANDF. Is that correct?
You mean this the name of the executable? Actually, I made a typo on here. Well, doesn't matter. Just as long as you're consistent. So I think in the slides I called the executable mand_c, I guess, and then I also execute with mand_c, like this. Is this the typo that you're talking about? I think mand_c. So as long as you're consistent, so the important point is you need to give output some name, and then you need to execute this code, the same name. As long as you're consistent, it's fine. I made a typo right now. Now, what I want to briefly mention now is that most of the time we don't want to write this compiling again and again and again in the command line to do the work. What we want to do is we want to write so-called makefile that can be used to repeat the same operation many times. So I don't want to, let's say I have several executables, so complicated way of combining my code. I don't want to always write this command g++ -10 and so on. It's kind of a lot of writing. So we typically create a makefile, and then all we do is to write make, and it does lots of things. For example, in this case, it just compiles the two codes, the Fortran and the C version. But in principle, it can do much more complicated things. So this is so-called makefile, which is a file that tells the system how to get executable from your source codes. Okay, it can be complicated source codes, many source codes in principle. So we're going to go later on into details of the makefile, but right now just the very basic concepts of makefiles. So typical makefiles consist of the following. There is a set of variables that are specified on the top. So this is just variable. We will define cc to be our compiler. For example, g++ -10. If you have different compiler, you will change this thing here. So different name of the compiler, you change it. But this is just a variable. And then F90 is Fortran, okay? And then you can use these variables later on here. For example, this is how we use in makefile. Dollar and brackets, cc, means I'm using the variable. And dollar brackets F90 means I'm using the variable F90 in makefile. Now, makefile is a set of rules. Basically, it's just a set of rules, and it always executes the topmost rule. So the topmost rule is this one, the first rule. Now, how do I know this is a rule? Well, this is a rule because it has this column here. Okay, so if it has column, then it means this is a rule, and the first rule in the makefile is going to be executed. Okay. In this case, the rule is called all, so it means by default, the rule all is going to be executed. Okay, and what does this rule mean? Well, it means that it will execute so-called mand_c rule and mand_f rule. Okay, we're going to discuss this later on, exactly these rules are set up. But for now, this month C rule is a rule which is specified here, and month F is a rule which is specified here. Okay, so once we see that we need to specify all, then the code will say, okay, oh, that means that we need to specify what on the left hand side is so-called target, on the right hand side is what is the source. Okay, and now we go recursively. Basically, we see month C, okay, needs to be specified. Well, fine, okay, let's go here, and then month C needs to be evaluated. So how do we evaluate this? Well, that is specified by another rule. And what is that rule? Well, that rule depends on monthc.cc, okay, the source code, and then basically this is the real command that is being issued into the system. Okay, this real command is do this. Okay, and we're going to use variable.cc. And then once we are done with this, we go back and we execute the second part of the rule, which is the target or what we need is month F, but depends on this particular file, and it needs to do this command in order to obtain the target month F. Okay, so this is the rule. Now there is another rule in this file which is called clean, and clean basically just removes everything that's unnecessary after this compilation. So let's say if you want a fresh compilation, then you might want to get rid of everything that you don't need or that was obtained during previous compilation. And so now you could also execute any rule you want, but then you need to give you need to give to a makefile an argument. So if I write make clean, it means that I'm invoking now this clean rule rather than by default all rule. So if I write make clean, I'm actually executing or invoking this rule here. Okay, but if I write make, then means that it's equivalent to saying make all. Okay, make all means it invokes the rule all, which is by default, and it will do this compilation. Okay, so this is the most one of the most convenient ways of storing the compilation information, so information about how to compile the code. We're going to use makefile from time to time. Most of this class is going to be based on Python. So in other words, in this case, makefiles are not important, but there are going to be some times when we touch on makefiles, and it's useful to know a little bit because it's kind of standard in both Linux and Mac. They both have this concept in the operating system. Okay, so Perl. I'm not gonna go into details of Perl. It's beyond this class. I mean, I used to in the past, but Perl is now kind of almost abandoned language. Do any of you remember CGI scripts? No. So it used to be very, very popular for web development. So there used to be something very, very important that almost all the webs used to have CGI scripts, and Perl at that time was the engine behind that, and used to be really important. But it wasn't very fast anyway. And Python kind of replaced. I mean, it has a very, very strong regular expressions. And therefore, many scientists in the past were using this for using regular expressions. Awk is another language. Awk and Perl were used for regular expressions. But now that we have Python, Python also has regular expressions, and somehow this is less useful. But the reason that I'm kind of flashing with it is because Perl is another interpreter. So the difference between there's the fundamental difference between the interpreters and compilers. Compilers are those types of languages which need to take source code, compile into an executable, and then execute. While interpreters are those which don't compile, but basically execute line by line. So basically, first it's executed this line, then it executes the second line, then it executes the third line, fourth line, fifth line, and it never compiles. It never really heavily optimizes the code. It always just executes line by line in some sense. And therefore, interpreters, of course, tend to be much slower than compilers, not surprisingly. And it turns out that Perl, for example, although it's powerful in terms of regular expressions, is extremely slow for scientific computation. And when we execute that, you will see that it's basically 1,000 times, 6,000 times or something like slower than C or Fortran. But I'm not going to go into details of how the language looks like. I mean, I can flash it here, kind of awkward, but it's one of the interpreters that some people use. And finally, I'm going to go into Python. That's that. But I guess Python will probably need to wait for next time because it's 6:20. Is there any question that anybody would like to ask? Any issue? It was too easy today, so that no questions? Too simple? Yeah, so for the homework, here we have homework, isn't it? So basically homework remains the same as the last time. So you have to set up your environment, like we discussed, installation. And then those codes that we downloaded, you should execute them and see if your system is set up properly and if you can actually execute and get those codes to work. Now, if your environment is not set up properly, hopefully at least you can get Python working. Then it's already well, 80% of the course is going to be you will be able to follow. But it would be nice if you can get C++ or Fortran working for optimization of Python that we're going to use in some of the lectures.
But the own version of the code, are we supposed to write it in a specific language or just Python is good enough? So so you're asking us to write our own version of the Mandelbrot code, right? So can we write it in Python or is it
any?
Okay.
Any. So if you're whatever you think you can do, I guess Python is probably the best choice. I mean, if you're familiar with C++ by some reason, you can write in C++. I mean, I'm not gonna this part of the homework I'm not gonna check. Okay, and the reason I'm not gonna check is because well, you will not be able to follow. You will not be able to do homework 2 or homework 3 if homework one was not done. So in some sense, anybody who is going to do homework 2 or 3 and 4, I'm pretty sure they managed to do homework 1, 2 as well. So I'm not going to check it. But you have to do it because that's essential to follow. Okay?
Yeah, so do we need to submit any any files? Okay.
No, this time no need. No, it's just for you. You have to set it up so that it works, and then you're going to be able to follow.
Sure.
Yep. Any other question? Okay. If not, thank you very much for coming. Hope to see you on Wednesday.
Thank you.
Okay.
Bye-bye.
See you, Professor.
Bye-bye. Thank you.
Enjoy.
Bye.
Goodbye. Bye.